All right, so what I'd like to do now is just start with the simplest example of conservation of linear momentum that I can think of. So I'll do an example of a jet impinging on a vertical plate. So let me see if I can write that quickly. Jet impinging on a vertical plate. So here's the picture. So let's imagine that we have a plate that's being and we shoot a fluid at it. So we've got, let's see, some jet of fluid that's traveling from the left to the right and hitting the plate. So let me just call the velocity in this direction. Oh, let me get a different color here. I'll call the velocity v, and let's say that the area, the cross-sectional area of the jet is A, and it's really meant to be water, but let's give it a density rho, and outside of that there's air, let's say. So I'll specify that the pressure outside of that is P sub A for atmospheric pressure. So what I'd like to know here is, so if I kind of have this intuition that if I shoot a jet of liquid at a plate and the plate bounces off in some particular way, so I'm going to assume, according to my drawing anyway, that what happens is the fluid divides symmetrically and basically leaves, vertically via either the top or bottom. So my intuition is that if I do that, that will impart a reaction force on the plate that is, if I assume that the plate is stationary, I think that I should have to supply some sort of force to the plate to make it stay in place. So what I'd like to do is try to estimate the value of that force. So I'm going to calculate the magnitude of F, or I'll call it F of X, or F in the component of force in the X direction. In this case, I sort of have this intuition that I'm going to have to apply a force that points towards the left, so I've drawn the arrow in that way already. So how would I calculate that using Reynolds transport theorem, right? So if I were to write out Reynolds transport theorem for this case, well, first thing I need to do is identify a control volume. So let me identify a control volume. There's not a unique answer here, but I'm going to choose the following control volume, and you'll see what's nice about this particular one. I'm going to draw this control volume so that it actually slices all the way into and past the solid plate. You can probably hear my kid in the background right now. Okay, so I'm going to write out Reynolds transport theorem for that case. So that says that, oops, let's get the black one out here. The rate of change of momentum inside our control volume plus the rate of linear momentum flowing across our interface has to be equal to the sum of external forces. All right, so let's see. I think the most difficult term here to handle is probably this one. So what is this, right? So this is the linear momentum per unit volume times the rate at which, basically the volume flow rate of that momentum across our control surface. That's what this represents. So V sub r, as a reminder, is the relative velocity. So what this means is the velocity of our fluid minus the velocity of our control surface. So if I look at my control surface, actually I suppose I didn't actually write it on here, but I'm going to actually make this a fixed control surface. So the control volume / control surface is not going to move. So that makes things a little bit easier. So this is now 0. And so this is actually just equal to the velocity of our fluid. Okay, so quick reminder here. This is two equations, right? So velocity has two components. And so this could be in the x direction or the y direction, and each one of those different directions will give you one equation. So it's important to point out this is actually two equations. It's important enough that I'm actually going to write it out. This is two equations. X component and a y component. So solving these problems kind of reminds me of like my days back in statics, right? So yes, this is two equations, but actually I'm a smart person and I actually recognize that the thing that I want to know, which was the force in the x direction, doesn't have anything to do with like the equation that would show up in the y direction. Basically, I'm looking to balance linear momentum in the x direction with some of the forces in the x direction. So I'm only going to write out the x equation here. So I'm going to write out, in the x direction, I can write out conservation of linear momentum, which would say that the rate of change of whatever this first integral is over our control volume plus the flux term, which is rho times velocity in the x direction times v dot n. Now v dot n, after you take v dot n, it becomes a scalar, but we have to keep kind of close track of like what the sign of v dot n is and what direction it points. So I'll come back to that term in a second. So the rate of change of total linear momentum has to be equal to the sum of external forces. In this case, there's actually different external forces. So I have atmospheric pressure acting on both the left and the right side of my red control surface. So on the left side, there's a pressure P sub A pushing over the entire area of our red. So I'll sort of circle it here with my laser pointer. There's a pressure that's pushing all along this left surface. But because of the way I've chosen my control volume, it's easy to see that there's an equal pressure acting on the other side over a portion of the control surface that's exactly the same size. So I've designed this control surface in a way that I don't really have to keep much track of atmospheric pressure. I will say that in general, unless there's something really strange going on where the pressure is changing on the front and the back side, often you can solve these kind of problems using gauge pressure rather than you don't really need to use atmospheric pressure. Like if I had solved this using gauge pressures, then atmospheric pressure would be 0 and I wouldn't even be talking about this. So a lot of times it is actually helpful to solve these problems using gauge pressure, where atmospheric pressure by definition is 0. In the future, I'll probably do that without even telling you, unless there's some kind of weird pressure variation on the front and back side, in which case that still shows up. Anyway, so I've designed this control volume in a way that these two things cancel right away. And then, of course, the other thing that's acting is our the force that we're applying to the back of the plate, which acts on our total, the total control volume that we've identified. All right, so the first term here, the rate of change of mass time, or the rate of change of this integral of density times velocity in the x direction over volume, that term is 0, not because any of the individual things are 0. It's just that these things are all steady. Like neither the velocity nor the density actually depends on time. this is a steady problem. And so the first integral is 0, and I really only have to worry about this term right here. So let me pull that over to the other page and finish this off. So the integral we needed to do was the integral over our control surface of rho times v in the x direction of v dot n dA, and that's equal to negative or minus the magnitude of our force Fx. So all that really remains to do is evaluate this control surface integral, which actually it turns out is not very hard at all. So why is it not very hard? Well, let's look at this. Okay, so we need to evaluate this integral over our control surface. In this case, none of the things that are in here actually vary over, our control surface. So let's go back to our picture. So really what I need to do is perform the integral in this region right here. And if our velocity is uniform, then we can just write everything that's in there as rho times v. So that's the velocity in the x direction on that surface, times v dot n, which is minus v. So why is it minus v? It's because the velocity is in the opposite direction of the unit normal. So let's go back to that page again one more time. So let me draw our unit normal here. So this right here is our unit normal. And so our velocity is in the opposite direction of that, which produces this minus sign. We multiply by, oops, get the right color here. We multiply by area, and that's equal to minus Fx. So you can solve pretty straightforwardly. So the two minus signs cancel here, and you find that the force acting on the object, its magnitude, is rho v squared a. And I actually never needed to use any information about mass conservation in this case, and I didn't need to use any information about the y component of the linear momentum equation, and that's that won't happen every time, but it happens this time because we made judicious choices about how we defined our control volume and such. Okay, so one other thing that I just want to point out, let's check the units. So this is the first time we've ever seen a force written in terms of a flow. So let's check out whether the units on this thing actually match up. So units of density are kilograms per meter cubed. The units of velocity are meter per second, and that appears twice. And the units of area are meters squared. So let's check it out. So if I check all that out, I end up with a kilogram. Let's see, I've got 4 meters on the top and 1 meter or 3 meters on the bottom. So that's just 1 meter left over, and then a per second on the bottom. So kilograms meter per second squared, and in fact, that is the definition of a Newton. If you can't remember that, just remember mass times acceleration gives force, right? So that is actually the correct unit, so we can sort of double check everything. So this is probably the simplest case of conservation of linear momentum that we'll come across, but it's, I think, a really instructive one to start with. I'll move on to some more complicated examples coming up.